So where do we start on this one? Okay, so let's start with parent graph, right? So what's the order in which we want to do the transformations here? Let's everybody click them all the way close, because we're going to look at some new stuff in just a second. You're going to want to really hear this. Say it again, Andrew. Okay, squish and stretch first, right? So we're going to dilate first. And then after we dilate, we talked yesterday about this, and this is, it's kind of a good way to think of it. If I add the one to the other side, you can think of this as being something like that, right? So the 2/5, that's going to be the dilation, right? And then when we're subtracting -3 from x and we're subtracting -1 from y, and so those are going to be the horizontal and the vertical translations of the dilated function, right? But we want to dilate the thing first, and then we'll slide it to where its eventual spot, right? So we start with our parent graph. This is what kind of graph are we looking at here? Parabola. So it goes through the origin, name some other convenient points. 1, 1, 2, 4, 2, 4, 3, 9. So right there. Okay, let's see how. Oh man, that's not very good. So there's our parent graph, right? If we're going to multiply this by 2/5, the point that we're using is not convenient to draw, but what would be the most convenient point to dilate? 525, right? So we're going to go from 525 down to 2/5. So what would the y value be of the dilated point? 10. Okay, so we're going to go over 5 and up 10. And then we'll go 1, 2, so back there. And then these points, we're just going to have to kind of estimate these. So this one, 9 would be at what? As a mixed number, what's that going to be? The point that started off at 3,9 is going to be what? 9, so 18/5. What is that? 3 and 3/5. So that guy's going to be, about there. Whoops, about there, kind of, right? So we get the idea. It gets squished, right? And then all we have to do is just scoot that point over. What direction? How far? Where am I scooting it? 3 left and down 1. Okay, and we got it, right? No big deal. So our final graph would just look like so 3 and 1.
So it's the opposite of the x.
Yeah, because remember what we're doing is we're comparing this to the standard form. The standard form is going to be a times the quantity x minus h squared plus k, right? So the value of k is -1. The value of h is -3, because we're subtracting -3, and a is positive 2/5, right? Okay, so we would just scoot the whole thing down to there, so that's where the vertex would go. All right, so next issue then.
Yesterday you had P in there. Yeah, right there.
Yeah, P was, and we called that our parent graph, right? So P just stood for whatever the parent graph is. In our case, it was, now how's that different from this? Because in this case, we're just saying it's x squared, right? So we're starting with, instead of calling that P of x minus h, it's x minus h quantity squared. Okay, it could have been, if this was a square root graph, it would have looked like, then it would have looked like a times the square root of x minus h plus k. But the x minus h is always going to be inside the function, whatever it is. Okay, it could be absolute value. You'll see some square root graphs on the assignment. You see some quadratics. I think those would be 3. What does, while we're on the subject, what does a square root parent graph look like? If we wanted to graph y equals square root of x. Well, what are some key points it goes through? Origin, okay. And then over 1 up 1. And we know we're just plugging in values. We're just making a t-table, really, aren't we? We're plugging in x values and calculating y values. So when x is 1, y is the square root of 1, which is 1. What's another convenient point? X is 4, y is 2, okay. When x is 9, y is 3, right? So, yeah, really, that's what it is, isn't it? It's kind of a rotated half of a parabola, sort of, right? And we'll, later on in the year, we'll talk about how we get to here from a parabola. Okay. Okay, but for now, let's have a look at something a little different. So let's start with our convenient parabola, will be our parent graph. And let's try something different. This time we're going to do something like this right here. We're going to, let's let h and k both be 0. So we're not going to do any kind of translations. Let's just focus on what happens if we multiply x minus h inside the function by b. So what we've done in the past, the last example we did, was an outside dilation, right? See the difference? Here the dilation factor is outside of the function, but here it's inside the function, right? So we're going to look at, once again, we're going to let h and k be 0 for a second. So we're just going to look at something like this. If f of x is our parent graph, f of x equals x squared, we're looking at something, we'll call it j of x. J of x is just going to equal the quantity bx squared. Okay. So what happens when we multiply x by a dilation factor inside the function? Well, let's see what happens. Let's make b 2, for example. So if b is 2, anybody want to make a guess what that's going to do? It's going to make it go bonkers. That's true. Make it wide, because it seems that makes sense, right? Because it's so you're correctly. What's your thinking on that, Seth? You've got some. I can see the wheels turning. So an inside dilation is probably going to affect the graph in which direction?
I said it's going to be wider than the other one.
Okay, but now let's compare this. Let's just kind of try to make an analogy here. When we did an outside, when we added a number outside of the function, that amounted to what? Like the k is what? What would we call that? So I see people doing this. What's the word for that? Vertical shift or translation, right? So when we add a number outside the function, it's a vertical translation. When we add or subtract a number inside the function, we got a horizontal shift, right? Okay, so let's make an analogy here. When we multiply outside the function by a dilation factor, it dilated it vertically. What do you think is going to happen if I multiply inside the function? It's going to dilate it horizontally. That's correct. Okay, so let's look at what happens though. This part's a little bit strange. If I turn this one on, look what it did. Okay, so it did something kind of strange. It pushed the points in instead of pushing them out. Okay? Now let's think why that might be. If I'm multiplying inside the function, now let's think about like a t-table here. If we're going to graph values of the parent function and then the dilated function. So here's x is f of x and then j of x. If x is 0, b is 2 in this case, right? So 2 times 0 is still 0, so 0 squared is 0. So both of those are 0. That point didn't move, right? The vertex stayed the same. But let's pick something like x equals 1. If x equals 1, f of x is just x squared. what number are we feeding to the x squared function when x is 1? Well, what's our input? 1, right? So we're squaring 1, and we get back 1. Now, what about down here? I'm multiplying, b is 2, right? Let's actually write that as 2, how about? When x is 1, what's the number that we're squaring? 2, right? You see why? Because I'm multiplying 2 times 1.
Oh, X.
Yeah, when x is 1, we're squaring 2, and so we're getting back 4, right? What x value would we have to input so that j of x is seeing 1 just like f of x did? Because we let b equal 2. Okay, so that's the function that we graphed here in green. Okay, you see what I'm saying here? When you think about a function, it's just like a machine. You're just going to input values, and it's going to do something and spit out output values. This is the parent graph is a squared graph here, right? So its job is to square stuff. It's going to square the stuff that we feed it. Okay. In f of x, whatever number we input, that's what the function is acting on, right? So if we input a 1, it's squaring the 1. But in j of x, we've messed with the machine a little bit, right? We're multiplying all of our inputs by 2 before they get squared, right? So when we're inputting a 1, the function machine is actually, it's just hungry. It doesn't care where the numbers come from. It's just going to process those numbers, right? So we input a 1, it actually sees a 2, and that's what gets squared, so it outputs a 4, right? Now, if we want the function actually to square a 1, what value of x would we have had to have input? 1/2, right? We would have had to have input a 1/2 because our input is always being doubled before we square. Everybody see that? So we would have had to have done something like this. We would have had to have input a 1/2 in order for its output to have been a 1. So when we multiply the input variable by a value, what we're kind of doing is we're accelerating the numbers that the function is seeing artificially, right? What is that doing? Well, in a sense, that means that we're squishing the function, doesn't it? Right? Because we're getting to values. We got to the value 2 twice as fast as we would have for f of x. On f of x, I would have had to go down a little bit to where x actually equaled 2 for us to get a 4 out of that, right? For the blue function, I only had to input a 1 because it was being multiplied by that 2. And so you get this opposite effect. Now, we saw the same thing with translations, though, didn't we? Right? When you first look at translations, people probably would have said, when you first look at translations, let me go back, right there. When you first look at translations, people probably would have said, well, if you want to shift this thing to the right, wouldn't you just add a value? Wouldn't h be positive? And you'd add, like if I want to go right by 2, I would just do x plus 2. Without thinking about it initially, everybody says that, right? The first time you think about it, and then you realize, okay, it doesn't work that way. Well, why didn't it work that way? It didn't work that way because you get this opposite effect inside the function, right? In order for us to actually input a 4, for example, here, if h is equal to, well, let's say h, we want to shift this thing to the right by 2, let's say, right? For us to shift this thing to the right by 2, that means that the x value that the function is seeing, like if, let's say I want to put in a 4, right? If I want to input a 4, the x value that the function is actually seeing, we'd like that to be a 6, wouldn't we? You see what I'm saying? So as you go to the right, we want to input a value of 6. But if I want to scoot the thing to the right, well, then the only way I'm going to get the value 4 that I would expect is by subtracting 2 from that input. So, I mean, it's kind of a confusing thing to try to say in words, but we saw what the impact was mathematically. Right? Inside the function, we had the opposite effect of what we predicted. right? We ended up subtracting numbers instead of adding numbers when we wanted to shift to the right. You can kind of remember this the same way. If we want to do a similar thing for dilations, if we want to stretch the thing out horizontally, we're not going to multiply by 2. We're going to do the opposite, or the inverse, I should say. We're going to divide by 2, not multiply by 2, right? So inside dilations are the inverse of what you would expect. If this number on the inside, which we'll call b, is a 2, that actually means you're going to compress it by that much. So that's the number you're dividing by, not multiplying by, right? When b is 2, we're dividing the x values by 2, which scooted this one, for example, from a value of 2. The original coordinates were 2, 4. The dilated coordinates became 1, 4. The x values were diminished. They were divided by 2. Okay, so what if I wanted to take my original red parent graph and I wanted to horizontally stretch it by a factor of 3? What number would I have to multiply by x? 1/3. Yeah, let's watch that. So if I go back, I don't know if I can do, I think I might have to go.
You recording?
I am recording. Thanks for checking. I think I have to go in half increments, so I can't do that. But if I go back to like 1/2,
Wow.
look what happens. I end up stretching it by 2. Okay? Make sense? All right, and we can do the same thing with other functions. This doesn't have to be an x squared graph. This could be, we could make this like a square root of x if we wanted. If that's a square root of x, well, there's our original parent graph, right? If I want to stretch this thing to the right by a factor of 2, well, that's what I just did, isn't it? Right? If b is equal to 1/2, look what I did. Here was a point that started off at 4, 2, and it got stretched out to the point with coordinates 8, 2. So the y value stayed the same, but the x values were stretched. Do you see that? Okay, so what do you think happens then? What if we want to do a combination of horizontal dilations and translations? What's that? Make a prediction. There we go. Okay. So now what's going to happen, do you suppose, if we want to, let's say we want to stretch it by a factor of 2, and we want to perform some horizontal dilation, like if I want to scoot it to the right by 2, for example, well, then I just make h equal 2. Right? If I want to scoot it up by 3, then k becomes 3. Right? All we did was same as before, we dilated it, and then we moved the dilated version of the graph. Okay? So try a couple of these then from the assignment. So I'll just put them up here. So let's try something like this.
Could you horizontally switch it and then vertically switch
Yeah,
it
we will.
and make it back to its original?
Yep. Oh, and which reminds me. Okay, I wanted to show you one other thing with this. So, thanks for bringing that up, actually. If we... So, you might have already seen this, but let's look at that last example, right? You tell me real quick, what am I doing to this graph? So if this is, we're starting off with the parent graph, f of x equals, for example, let's say x squared. What did I just do? Okay, but I want you to tell, in terms of, use our vocabulary for transformation. So really, what do we got? We got vertical and horizontal, we've got dilations and translations.
Horizontally.
So I horizontally stretched by a factor of 3, right? I multiplied inside by 1/3, which means I have to look at the reciprocal, right? It's the reciprocal action, which means I'm going to stretch horizontally by a factor of 3, okay? If I stretch a parabola horizontally by a factor of 3, what do you suppose that is equivalent? Because, now this doesn't work for all functions, but because the parabola has symmetry here, what does that amount to in terms of a vertical stretch? Because the two things overlap, right? Now let's look at a quick picture of this. So if we've got a parabola and so here's my parent graph. Something like that. If I stretch this thing out by a factor of 3, then for example, this point right here is going to end up being right there, right? This point right here is going to be out, instead of being at 2,4, it's going to be at 6,4, right? So it's going to be clear out here. That's equivalent to doing what to my graph vertically? Squishing it. Squishing it by how much?
Factor of 3.
No,
One.
not a factor of 3. Now, if I drew this very well, which I didn't, so this point right here would normally be at, let's see, this, now it's at, it went from,
1/9.
yeah, it's 190, right?
Oh, so that's.
So this one's gonna go from, this one, here, let's write some coordinates down. So this one went from
2,4 to
1, 1 out to the point
3,1.
3, 1, right? This point went from 2, 4 out to the point 6, 4. Okay, this point up here, way up here, went from the point, I don't know where this is, but this one went from the point 3, 9 out to what?
9/9.
Out to 9, 9. Okay, where would that point have started off if I were gonna vertically squash this thing? So a point that ends up having an x coordinate of 9 would have originally had a y coordinate of 81. Would have been way up there, right? Would have been way up there. And so I would have had to squeeze that one clear down from 981. What did I have to multiply the y values by? To go from 81 down to 9? 19, yeah. Everybody see that? Can we show that mathematically? Yeah, pretty easily, right? What are the steps if I apply properties of exponents here? I've got a product of 1/3 times x. If I have a product to a power, what's the property of exponents that I can use? Like if I have something like a times b to the m, what's that equal to? Yeah, it's just a to the m times b to the m. So if I'm multiplying, I can distribute the power, right? So this would just look like 1/3 squared times x squared. Well, what's 1/3 squared? 1/9. So another way I could write this, if I wanted to, I could write g of x as 1/9 times x squared. So what's being done there if I write it like that? Is that an inside or an outside dilation? That's outside, right? That's not inside the function, that's being multiplied by the parent function. So an outside dilation of 1/9 is doing what? That's like yesterday's homework. What's that do? If I multiply a function by 1/9, I'm vertically compressing it, right? By a factor of 1/9. So you can, what you can see about this then is that horizontal and vertical dilations are equivalent. You're just looking at it from a different perspective, right? We're tracking the points. When we horizontally dilate something, we're stretching the points horizontally, so the points are not moving vertically. It's like they're sliding along horizontal wires, right? If we're vertically dilating a function, the movement of the points from before to after is going to be vertical, so they're sliding along vertical wires, right? But they accomplish the same thing, don't they? So what that tells us, and this is kind of a higher level topic, but it's nice to kind of just think about this stuff. We're not going to really get to that point this year. But in math, this happens frequently. There are times in math when you can get an answer by doing different types of transformations, but you choose the one that's easiest to work with. And that goes all the way up to probably the most complicated math that humans have ever invented would be the topological math that string theorists use in physics, where they're looking at these multidimensional manifolds and trying to understand the way the universe works. And they see kind of the same thing going on. Like if they look at, string theory tells us that our universe, we have 3 extended dimensions in our universe, which we all know about. We can go side to side, front, back, up and down. And that's how we can locate anything in our universe on a large scale. But string theory says, and it's probably going to end up being right, that there's also these 7 really tightly wound dimensions that are on a very, very small scale, and they're sort of curled up. And you don't ever see the effects of these because they're curled over themselves on such a small scale, but it's consistent with all the predictions and the laws of physics. And so in order to really understand string theory, we've got to understand these other extra dimensions that we don't ever really interact with because they're so small. But the math that goes with that, these scientists, these big-time physicists, and there's only a handful of people in the world who even understand this. And they're kind of getting old, so they're trying to teach the younger generation this math. It's big-time stuff. But one of the things they have to deal with are all these transformations, just on a whole different level. They're called Calabi-Yau spaces, or these 7-dimensional spaces, and they have to be able to transform these to they have to look at them from one perspective, and then do some math, and then transform back to the perspective that represents the universe. It's kind of like in topology, what do you think is more similar? You tell me which two objects are more similar. A coffee cup and a glass, or a coffee cup and a hula hoop. Which two seem more similar? The coffee cup and the glass probably seem more similar, but topologically, you're right, it's the coffee cup and the hula hoop. And the reason they are is because the coffee cup has a hole in it, has a handle with a loop, and the hula hoop has one hole in it. And topologically, that's much more important than the fact that they both hold liquids. They kind of look the same from the outside. And so that's this is sort of akin to saying, we're going to take this coffee cup and we're going to morph it into a hula hoop to do some calculations because it's easier to do when it looks like that, and then we'll morph it back into a coffee cup when we're all done. This is out there, but the reason I bring this up is it's sort of the same kind of a thing you see just at a really infant level with problems like this. Sometimes it's easier to think of something as a horizontal transformation or a vertical transformation, and you have the freedom to do that, right? Okay, last issue. What if we wanted to do something like this? You bet. Yeah, before Christmas, we'll take a day and just geek out with black holes. Yeah.
It can get bigger. It's limited.
Okay, so here's a sample of a problem from the second of the new assignment. So what if I wanted to choose the graph of this? What are we going to do? Just let's talk ourselves through what's our thinking on this one. So if you don't have your Chromebooks closed, close them up. Yeah, I don't mind you guys having them out, but I insist that you close them now because I want you to see this. So what's going on with this one? What are the things we're going to do and in what order? We're going to solve it. We're going to graph it. But what do I have to, what are the things that are being done, and then we'll put it in the proper order.
Maybe distribute the.
Okay, now I could, but we really don't want to. It makes it harder to do that because I'm going to force you to do something like that in a second, and they're a little tougher. Right? What are the three things that are being? What's one transformation that's being done to our parent graph right there?
Dilation.
What kind of dilation? So we're horizontally dilating. What are we doing horizontally? Stretching or squishing?
Stretching.
We're stretching by a factor of
3.
Good. So we're stretching horizontally by a factor of 3. What else are we doing?
Moving left 1.
Moving
Down 1.
moving down 1
Left 1.
and left 2. Okay. So what's the order clearly here in which we want to do these things?
Dilation.
We're going to dilate first, right? Because then it's easy to dilate the graph when it's the parent graph with a vertex at the origin. Easy to do, right? Once we've dilated it, then we just slide it a little bit horizontally and vertically, and we're done, right? So what's that going to look like? Well, we want to find, if we're looking for the right answer, then we're looking for, we're looking for the graph that has a vertex where?
It's going to be
-2, -1. So that's the right vertex, but has it been dilated appropriately? No, where should that point actually be right there? It should be stretched out so it's 3 times as far to the right from the vertex as it was originally, right? So it should be, yeah, it should be over here at, right there, shouldn't it? Everybody see that? This point should have been stretched from 1 out to 3 away from the vertex. Now, if we were graphing this off by hand, we would have dilated it first and then translated it, right? But we're having to pick the graph that's already been dilated, right? So you could do this on graph paper and just match them up, and maybe we could even just think of it this way. So that's where the origin should be if it's not dilated, or it's not translated. From there, this point should be, instead of being at 1,1, it should be at 3,1, right? So we just have to find that graph. Oh, not it, right? Not it. Oh, look right there. Oh man, how about that one right there? That looks pretty good, right? That's it. Okay. So that's our.
Do you think you could
That's our answer.
scroll it without that moving? Right.
Without what?
Without that moving.
What do you mean?
Without that moving.
Without the red thing moving, like keep it fixed on the screen.
That'd be cool. You could do that.
Well, isn't that what I'm doing right now?
No, the red thing's moving with the screen, like. No, it's not.
Okay, it is?
With it staying
Oh,
on.
staying. No, I can't. Can't do that.
You can figure that out.
I don't think
Wait, hold on, go.
He's saying.
I think you forgot to choose the. No, you did.
so. Okay, so next question. So what happens? Yeah, what if we distribute? So what if we have something like this? Let's go back to here. See ya.
We're excusing 25.
Yeah, we are. Yeah, we're good. So what if we do something like this instead? So let's look at this guy. Let's go back and let's make H and K 0 again. Oops. H and K are 0. Let's make B 1/2. And let's go back. Now let's look at a graph like this, where we're multiplying the B times the X, but it's not being multiplied by X minus H. So it's like we've distributed maybe, right?
Yeah.
Okay, looks the same so far, doesn't it? Right? Looks the same as it normally would. But now watch what happens if I make H like positive 2, for example. So we're subtracting positive 2. Does it scoot to the right by 2?
Oh.
It didn't. It scooted by 4. It didn't scoot by 2.
So you're not
Okay.
allowed to do what you're
You're not. What you have to do in those situations, let's think about the order of operations, right? If we're looking at something like this, if we're looking at something like g of x equals 1/2, is that what it is, 1/2? Yeah, 1/2 x minus 2 squared plus 1, or minus 1, I guess it was. Okay, this acts very differently, right? Now, we're not just subtracting 2 from x, we're subtracting 2 from 1/2 x. So here's the way you have to think about this one. This is very different. So this time what we're going to do is we're going to ignore the dilation factor, and we're just going to translate this thing like we normally would. So we're going to put this, it's going to be a regular x squared graph that's going to go right by 2 and down by 1, okay? The effect of multiplying just the x variable, and we'll talk more about, we're running out of time today, but we'll talk more about this later. The effect of multiplying just the x variable then, by itself, is that we're going to dilate everything relative to the y-axis. So what that means is we're going to take every point on our translated graph and we're going to move it twice as far away from the vertical axis, from home, from the y-axis. Okay, we'll deal with that a little bit.